Dear students, welcome to Tungal online classes. Next, we shall derive the expression for effective EMF and internal resistance of a parallel combination of the cells. Yes, let us consider two cells of EMF E1 and E2 and the internal resistances R1 and R2 which are connected in a parallel combination like this. Let I1 is current sent by the cell E1 and I2 is current sent by the cell E2, so that the total current because of both the cells is equal to what? I, which is equal to I1 plus of I2. Yes, and the second figure indicates the equivalent circuit of a parallel combination of these two cells. Let EP is effective EMF of this parallel combination and RP is effective internal resistance of the parallel combination. Yes, since both the cells are connected in parallel, the terminal potential available will be same. Here also the terminal potential will be V, here also terminal potential will be V, which is also equal to the terminal potential when we have the parallel combination of both the cells. Yes, and we have the general expression for the terminal potential is equal to what? V is equal to E minus of I into R. Okay, I can simply write I into R is equal to V minus E minus of V. I can write I is equal to what? Capital E minus of V divided by R. This is the general expression for current flowing through cell. Yes. Now, when I consider the first cell here, I can write the expression for electric current through the first cell. I1 is equal to what? I1 is equal to E1. E1 is EMF of the first cell minus of V whole divided by R1. R1 is internal resistance of the first cell. Yes. Similarly, for second cell, I can write the expression for electric current I2 is equal to what? E2 minus of V. E2 minus of V divided by R2. R2 is the internal resistance of a second cell. Yes. Then if I consider the effective combination of both the cells here, I can write the expression for the current flowing through the combination of the cells as, let this be equation number 1, let this be equation number 2, and considering the equivalent circuit, I can write current is equal to I, that is sum of I1 plus of I2. I can write it as capital I is equal to what? That is EMF is EP minus of the potential to terminal potential is again V divided by the resistance of the combination. I have written it as RP, and we know the total current I is equal to sum of I1 and I2. Hence, I can write it as I is equal to I1 plus of I2. Let this be equation number 3. Substituting equations 1, 2 and 3 in this equation, I can write it as EP minus of V divided by RP is equal to I1 is what? E1 minus of V divided by R1 plus of E2 minus of V whole divided by R2. Yes, let us simplify this. The denominator is R1 into R2. Here we will have E1 into R2 I will get minus of V into R2. This R1 I will multiply to the numerator here. So I will get E2 into R1 minus of V into R1. Yes, so this I can write it as E1 R2 plus of E2 R1. Yes, minus of V into R1 plus of R2 whole divided by R1 into R2. Yes, in LHS I have EP minus of R whole divided by RP here. So, EP minus of V whole divided by RP. Let me separate this. I can write it as EP divided by RP minus of V divided by RP, that is equal to, I can write the same equation as E1 R2 plus of E2 R1 whole divided by R1 R2. I am just taking common outside R1 R2 minus of V into R1 plus of R2 whole divided by R1 into R2. Yes. Now let us compare the LHS and RHS. Consider the coefficient of V here. Considering the coefficient of V, I can write 1 divided by RP. 1 divided by RP is equal to what? R1 plus of R2 whole divided by R1 into R2. Yes. the same thing can be written as 1 divided by Rp is equal to 1 by R1 plus of 1 by R2. This is the expression for effective internal resistance of a parallel combination of two cells. Okay. The same thing can be extended for n number of cells. I can write as, if you have n number of cells, the effective internal resistance of those cells is given by 1 by R1 plus 1 by R2 plus 1 by R3 up to, I can write up to 1 by Rn. This is the expression for the effective internal resistance for parallel combination of n cells. Okay. So, this is about the internal resistance. Then, to get the effective EMF, again consider this part, right. So, where I have EMF, compare these two terms here. I can write EP divided by Rp is equal to what? E1 R2 plus of. So, this term I will equate it with this E1 R2 plus of E2 R1 whole divided by R1 into R2. Okay. This Rp I will take it to the right side. I can write this as E1 R2 plus of E2 R1 whole divided by R1 R2 into Rp. Okay. So, LHS remains as EP here, that is the effective EMF of a parallel combination. This Rp I will substitute here. Rp is equal to what? R1 R2 divided by R1 plus of R2. So, I can write it as E1 R2 plus of E2 R1 whole divided by R1 R2 into Rp is equal to what? R1 R2 divided by R1 plus of R2. These two get cancelled here. Hence, I can write EP as EP is equal to E1 R2 plus of E2 R1 whole divided by R1 plus of R2. This is the expression for effective EMF of a parallel combination of two cells. Yes. Then observe this here. This equation we can also write it as EP divided by Rp can also be written as, by simple mathematical simplification, I can write it as E1 divided by R1 plus of E2 divided by R2. If I take the LCM, again I get the same term here. Yes, this is the general expression for effective EMF of two cells. The same expression can be extended for n number of cells, that is combination of n number of cells. I can write EP divided by Rp is equal to E1 by R1 plus of E2 divided by R2 plus E3 divided by R3. I can write it up to En divided by Rn. This is the general expression for effective EMF of a parallel combination of n number of cells. These two are very simple derivations which can be asked for 5 marks. Yes. Next, let us discuss very important concept of Kirchhoff's laws. Yes. So far, whatever theories that we have discussed, that is Ohm's law, this series and parallel combination of resistors and cells, whatever equations we have arrived at, those equations may not be sufficient to solve the complex problems, right. So, practically we come across complex circuits in which only these laws are not sufficient. Yes. So, to solve such difficult problems, Kirchhoff's laws are very useful. Yes. There are two Kirchhoff's laws. The first one is Kirchhoff's current law. The second one is Kirchhoff's voltage law. Yes. The Kirchhoff's current law states that, so if we have a junction, through which the different currents are passing. Yes. Let us consider I have junction point P here. Let us consider the current I1 is entering the junction P, current I2 may be going out of the junction P. So, here let us have the currents I3 and I4. Yes, the Kirchhoff's current law states that the net electric current at the junction at a node is equal to 0. Yes, see here if I should have the exact current at point P is equal to 0, whatever input current is there, that must be equal to the output current. Okay, what are the currents coming towards point P? I1 is input current and again I have I3 input current. The sum of I1 and I3 must be equal to what? the sum of I2 and I4. So then only I will have the electric current at the junction P is equal to 0. So for this the input current must be equal to what? The output current. So here I have 4 currents here. Out of 4 currents, 2 are input. So the sum of input current, that is I1 plus I3, must be equal to what? I2 plus of I4. Yes, this is the Kirchhoff's current law. Yes, the net electric current at a junction is equal to 0. That is, the input current at the junction must be equal to the output current through the junction. Yes, this is the Kirchhoff's current law. Okay. And for understanding Kirchhoff's voltage law, let us consider a circuit here. Let me consider cell E1 here. Let R1 is its internal resistance. Let us have an external resistance of resistance R. Let us take another circuit here, another cell. Yes, its EMF let it be E2. Let its internal resistance is R2 here. Okay. The Kirchhoff's voltage law states that the net sum of EMFs and the potential drops through a closed circuit is equal to 0. Yes. So for this, let us name the circuit here A, B, C, D, E, F I will take. Okay. And let us first consider the circuit closed path A, B, C, F, A. Let us consider this is the first closed path. Okay. And here, for understanding this, we shall assume the direction of current is clockwise. We are free to assume, either we can assume it clockwise or we can assume anti-clockwise. Okay. In second circuit also we shall assume the current is flowing clockwise. Okay. And there are some sign conventions here. Yes. What happens? See here, we are moving in clockwise direction, that is from A to B, B to C, C to F and F to A. Okay. Whenever we are moving along this path, if this direction of current, so let us consider whether to consider the EMF plus or minus, when to consider EMF plus and when to consider EMF minus. Okay. So now our assumed direction of current is clockwise. So we are assuming current is flowing from A to B, B to C, C to F and F to A. Okay. But actually the conventional direction is from the positive terminal. So let us consider this is the current I1. I1 is current sent by the EMF E1, and let us consider here also we have another cell. I2 is current sent by the cell E2. Okay. This I1 will come from A to F. Yes. Again here this I2 will come from E to F. So here I have input current of I1. Here I have input current of I2. At the junction F, both are input currents. Hence, here it should go out. So here I will have the current of I1 plus of I2. The current leaving this junction will be I1 plus of I2. So the current passing through resistance R is I1 plus of I2. I hope it is clear. Okay. So now let us consider the sign conventions. See here, I am moving from A to B, B to C, C to F, F to A. Along this assumed direction, if the assumed direction is flowing from higher potential to lower potential, that EMF we take it as a negative. Okay. My assumed direction is from A to B, so it is moving from a higher potential to lower potential. So this EMF I should take it a negative here. Okay. Then what about the potential drop? Wherever I have resistances, there I will have potential drop. Okay. So here I have current of I1. So here I have current of I1. The current flowing through this internal resistance R1 is I1, and the direction of this current is in the opposite direction of assumed direction. Yes. So assumed direction is clockwise, but this current is coming in opposite direction. The potential drop in such cases, when the direction of actual current is in opposite direction of assumed current, in that condition this potential drop we take it as a plus. Yes. Again, next consider this R here. Let us come from A to B, B to C, from C to F. While moving from C to F, the current flowing through the resistance R it is in the opposite direction of a clockwise direction. We have assumed the clockwise direction, but the current is coming in opposite direction. So, the potential drop because of this current across this resistance will be positive. Okay, I repeat again. Yes, the EMF of the cell will be taken positive if the assumed direction is moving from lower potential to higher potential. Yes, but in this case the assumed direction, that is from A to B, we are moving from higher potential to lower potential, so we should take it negative. Okay. Similarly, the potential drop is taken positive if the actual current is flowing in the opposite direction of assumed current. Okay. So, assumed current is from A to B, but actual current I1 is coming in opposite direction. So, the potential drop because of this I1 across this resistance R1, we take it plus here. Yes, similarly, when we move from C to F, the assumed direction is from C to F, but the current is coming in from F to C. So, this potential drop also we take it positive. So, considering the loop, the closed loop, that is A, B, C, F, A. So, this EMF, I am assuming the clockwise flow of electric current, this EMF is from higher potential to lower potential, that we take it as negative, minus of E1 I will write. Okay. Then the potential drop because of this internal resistance R1, that I take it as plus of I1 into R1, because it is in the opposite direction of our assumption. Similarly, this potential drop, so we are moving in clockwise direction, current is coming in opposite direction, that we take it as plus. And what is the magnitude of that potential drop? The current through this resistance is what? I1 plus of I2, is it not? I1 plus of I2 into the magnitude of its resistance is what? Capital R, and that is equal to what? 0. Yes, the net sum of EMFs and the potential drops is equal to 0. By considering this, we can write, I can take it E1 right side, I can write I1 R1 plus of I1 plus I2 into R is equal to what? E1. Yes. So, this is the expression for the Kirchhoff's voltage law. The Kirchhoff's voltage law states that the net sum of the EMFs and the potential drops is through a closed loop is equal to 0. Okay. Similarly, if you consider the loop, for second loop we shall take, that is F, C, D, E, F. Let us take F, C, D, E, F. Okay. Again we shall assume the direction of the current is clockwise. Okay. From F to C we have a resistance here. Yes. And the potential drop is in the same direction of our assumption. So, this we take it minus here. Yes. So, the potential drop through R is what? Minus of I1 plus I2 into R. Yes. C to D we do not have any component. From D to E, there is an internal resistance, and here the current is what? This is I2. Yes. So, this potential drop, this direction of this I2 as well as the assumed direction, both are same here. Hence, again that potential drop I take it as a minus. That potential drop is equal to what? Minus of I2 into R2. That is the potential drop across a second internal resistance R2. Then consider the EMF here. The assumption is in clockwise direction, and this direction is moving from lower potential to higher potential. Hence, this EMF I should take it plus. Whenever the direction is from lower potential to higher potential, that EMF I take it as a plus. So, this is equal to what? 0. Yes. Again, by simplifying, I get E2 is equal to what? I2 into R2 plus of I1 plus I2 into capital R. Yes. This is the expression for Kirchhoff's voltage law for second loop. Yes, whenever we solve numerical problems, this concept will be more clear. Next, let us derive the condition for balanced Wheatstone bridge. Yes, this is one of most regularly asked questions for 5 marks. Yes, Wheatstone's bridge consists of 4 resistors P, Q, R, S, out of which 2 resistors, the 2 terminals are connected by a galvanometer, and remaining 2 terminals are connected by external source of voltage. Yes, and Wheatstone bridge is said to be balanced when the current flowing through P and Q is same, and the current flowing through R and S is same. And for that we apply Kirchhoff's junction law, that is Kirchhoff's current law at point P. Yes, so that the current flowing through this Ig is equal to 0. So the condition for balancing of Wheatstone bridge is that the current through this galvanometer must be equal to what? 0. That is Ig must be equal to 0. Yes, it is very simple derivation. Let us derive the same here. Okay, let us consider the loop A, B, D, A. Yes, here the input current I is divided into I1 through A to B, then the current through galvanometer is Ig, the current through resistor R is I2. Okay, then after having the current through the galvanometer, here the current is I1 minus Ig, and at node D there are two inputs current, that is I2 and Ig, so that the output current is what? I2 plus of Ig. Again after point C we have the total current of I, which is sum of these two currents. Yes, so let us assume the current through this loop A, B, D, A as clockwise, so that the potential drop at resistor P, so that is taken as minus here. So I can write, applying Kirchhoff's voltage law for this loop A, B, D, A, the potential drop at resistor P is what? Minus of I1 into P. Then we shall move from B to D. The current passing through galvanometer, let us write it as Ig. So the potential drop at this galvanometer, G is the resistance of the galvanometer, so that is also in the same direction. This potential drop is also in the same direction of assumption. So that potential drop we write it as a minus of Ig into capital G. Okay, then when we move from D to A, the current is coming in opposite direction of assumption. So the potential drop because of this I2, we shall take it as a plus here. So that I write it as plus of I2 into R, and we don't have any cell in this path, so we do not write any EMF, and this is equal to what? 0 according to Kirchhoff's voltage law. And we know the condition for the balanced Wheatstone bridge is the current through galvanometer must be equal to 0. Yes, hence substitute Ig is equal to 0 in this. I can write minus of I1P plus of I2 into R is equal to 0. I can write I1P is equal to what? I2 into R. Let this be equation number 1. Yes, similarly we shall consider the loop B, C, D, B. Yes, and again we shall assume the clockwise movement of the current here. Then we shall move from B to C. B to C, the direction of current, that is I1 minus Ig, it is in the same direction of our assumption. So the potential drop across this resistance Q, that is I1 minus Ig into Q, that is taken as negative. Okay, because the actual direction of the current as well as assumed direction of current both are same. So that potential drop we write it as minus of I1 into Ig into Q. Yes, then we shall move from C to D here, but the current is coming in the opposite direction of our assumption. So that potential drop we take it as plus here. The potential drop at resistance S is equal to what? I2 plus of Ig into S. Yes, then let us move from D to B. The current is again coming in the opposite direction. So that potential drop because of this Ig, I write it as plus Ig into capital G is equal to 0. Again in this path also we don't have any EMF. Okay, so let us substitute Ig is equal to 0. So we get minus of I1 into Q plus of I2 into S is equal to 0. This I can take it to the right side, so it will be positive here. I1 into Q is equal to what? I2 into S. Let this be equation number 2. Okay, consider equation number 1 and 2. Let us divide LHS divided by LHS and RHS divided by RHS. That ratio will be same. So by dividing the LHS of this equation by LHS of second equation, I can write I1P divided by I1Q is equal to the ratio of RHS, that is I2 into R divided by I2 into S. These two get cancelled here. Hence we get the condition P by Q must be equal to what? R by S. Okay, so the ratio of these two resistances must be equal to the ratio of remaining two resistances. Next, let us discuss the concept of electric energy and power. Okay, so whenever we are using any electric devices such as electric bulb or a heater or any other device, the work is extracted by supplying some electric current through the component. Okay, so there is some continuous flow of electric current through the electric devices. So to maintain that, let us consider a symbolic electric device like this. Okay, so this can be either bulb, this can be heater or any other electric device. Okay, so whenever we are using this electric device, there must be some flow of electric current through this device. Okay, to maintain the constant flow of this electric current through this device, to extract the desired work, there must be some external energy required. Okay, so this device will be connected to the source of a potential difference. By supplying the potential difference, there is flow of electric current through this device. Let us consider the potential difference applied, let it be V. Okay, so there is constant potential difference of V is applied, because of which there is a uniform electric current of capital I is flowing through the device, and we are getting a desired output work. Okay, so to maintain this uniform electric current through this device, there is some external work done. Yes, to do that work, there is some energy required. Okay, that energy required to maintain the constant current through any electric device by supplying the potential difference is called electric energy. Okay, so whatever electric energy is given to this device, equal amount of work is done, right? There will be some losses, that is inevitable. So electric energy is simply the energy required to maintain the constant current of capital I through any electric device to get the desired output by supplying a potential difference. Okay, that is the basic definition of electric energy. Now let us write the expression for this electric energy here. See here, the current flowing through this electric device is what? Capital I. So there will be some charges flowing through this device. So let us consider, I know the definition of electric current is equal to what? Q divided by T. Okay, so after certain time of T, the number of charges flowing through this device, let it be equal to Q. This can be written as I into T. Okay, so whenever I say there is flow of electric current, there will be some charges flowing through this device. That magnitude of that charge flowing through the device is equal to what? Q is equal to I into T. Okay, but there is potential difference across ends of this device, so there will be some work done. In the previous chapter we have seen, whenever there is potential difference and the charges are passed through that potential difference, there must be some work done. That work done is given by the potential difference into charge. Okay, just replace this Q by I into T. I can write W is equal to V I T. Okay, this is the mathematical expression for electric energy. Yes, then by the basic definition of power, power is work done per unit time, or it is the energy consumed per unit time. Whatever energy is converted, same amount will be converted into work. Okay, so by that definition, when we say electric power, it is the energy required per unit time to maintain the current through any electric device to get the desired output work. Okay, so by the basic definition I can write P is equal to, so whatever this work done is there, same work done will be equal to what? The electric energy, that is also equal to VIT. Okay, so this power is equal to what? Work done divided by time. So this is also equal to electric energy divided by time. So I can write P is equal to VIT divided by T. So I can write P is equal to what? V into I. Yes, electric power is simply the product of the potential difference and current flowing through the circuit. Yes, this is basic meaning of electric energy and power. Yes, then the unit of electric energy, is joule. Yes, and the unit of power is it is joule per second. that is nothing but watt. Yes. So here the unit of electric energy is joule and the unit of power is watt. Just now we have seen the SI unit of electric energy is joule and that of electric power is watt. Okay. But conventionally for electric energy, we are using the unit of kilowatt hour. Okay. Just now we have written power is equal to what? Electric energy per unit time. I can write electric energy is equal to power into T. Okay. The unit of this energy can be written as, the unit of power is kilowatt. Okay. Kilowatt into time is taken as hour here. Okay. Then so kilowatt hour is the conventional unit of electric energy. Yes. And how much is 1 kilowatt hour in terms of joule? Yes. So that I can write it as 1 kilowatt hour. It can be written as 1 kilowatt is nothing but 1000 watt. Okay. Into 1 hour I can write it as a second here. In terms of second, if I write it, it is equal to 3600 second. Okay. So this I can write it as 1000 watt is nothing but joules per second into 3600 second. Second get cancelled here. So I can write 1 kilowatt hour is equal to, yes, 3600 into 10 to the power of 3 joules. Okay. That is 36 lakh joule is equal to 1 kilowatt hour of electric energy. Okay. And for power, the conventional unit of electric power is a horsepower. We use it as a horsepower, and 1 horsepower is equal to 746 watts. Okay. So this is the equivalent value of 1 horsepower. This is the regular unit for electric power. Okay. Now let us understand the working of a meter bridge. This is also called slide wire bridge. Meter bridge is a practical form of a Wheatstone's bridge that works on the principle of balancing of Wheatstone's bridge. Okay. Before knowing the working, let us understand what is the construction of this meter bridge. A meter bridge consists of 1 meter length wire, usually made up of manganese or constantan. So in this case, AB represents that 1 meter length wire. So the length used is 1 meter, hence we have the name of meter bridge here. Okay. The ends of this metal wire are connected to 2 thick copper strips here. This is first copper strip and this is another copper strip here, and there is in between there is a long thick copper strip here. Okay. And there is gap between the terminals of these 2 copper strips as well as these 2 copper strips, in between which we place the resistors. Okay. The terminals of these 2 copper strips are connected by a known resistor of resistance R. Okay. And these 2 terminals are connected by another resistor whose resistance is S, and we have to find out this value of S. Okay. On the other part, here we have a meter scale to read the length here. Okay. Then the ends of the metal wire are again connected to an external source of potential difference through a key like this. Okay. This will act as a source of electric current. Okay. Then so in between, at the midpoint of this central copper strip, there is another wire connected to a jockey. Okay. This jockey is a small metal rod which can be used to make the connections here. This jockey can be placed anywhere on this line. We can slide the jockey on this metal wire, right? So wherever we get the equilibrium reading, that is 0 reading of the galvanometer, at that point we call it as a C. Okay. Then how it is practical form of Wheatstone bridge here? Here I have drawn the Wheatstone bridge. Let us compare both the figures here. Okay. So whatever this metal wire is there, AB, so that AB is lower part of this Wheatstone bridge. Okay. Can you see it here? This is the left terminal A, this is the right terminal B here. Okay. And this is point C. This is point C. Wherever I place the jockey, that will form a point C. Okay. Then what is this resistance P? Look at this. Whatever this part of the wire is there, AC is some metal wire. Okay. This is having length of L. So we know any metal wire is having some resistance. The resistance of this metal wire, this part of the wire, that I am writing it as a P, okay, and the resistance of remaining metal wire is of length CB, okay. So total it is 100 centimeter. The length of this AC is L centimeter, hence the remaining length, that is C to B, will be equal to what? 100 minus of L, yes. And the resistance of this part of the wire, that I write it as a Q, okay. Then the upper part, the upper portion, whatever resistance I am applying here by using the resistance box, that resistance box is here. So this resistance box is between the points A to D. So this is your terminal A, this is your terminal D. Between the terminal A and D, we have the resistance of capital R, okay. Then between D and B, between D and B, this is point D, this is point B here. Between D and B, we have the unknown resistance of S, okay. Then again, between point D and C, this is point D and this is point C, we have the galvanometer. Here also I am showing a galvanometer between point D and point C. And how to find point C? When the key is closed, current starts flowing through the circuit, okay. This current will flow through this wire also, as well as through this path also. There is current flowing through both the paths. See here the current is flowing in upper route also, the current is flowing in lower route also. So here also there will be current flowing in both the paths, okay. So I will just start from the point A, I will slide over this wire, I will stop this jockey at the point C when there is no deflection in this galvanometer. The deflection of this galvanometer is 0, okay. So that is the balancing condition for working of this Wheatstone bridge. In this example, I am taking that point here, that is point C, okay, and at that point, using this meter scale, I will measure the length, okay. If it is L, the remaining length will be equal to what? 100 minus of L, okay. Then how to find out the unknown resistance here? Look at this. In previous class, we have seen the balancing condition is what? The ratio of the left part of this Wheatstone bridge, that is R by P. Just names may be different, do not get confused. The ratio of the left resistances must be equal to what? The ratio of the right resistances, that I can write it as S divided by Q, okay. Now I know the value of R, I don't know the value of S, but what about resistance of these two wire parts? That I don't know, but we know the property of the resistance, that is the resistance of any metal wire is directly proportional to length of that metal wire, okay. I have said the resistance of this metal wire AC, that is equal to P, okay. So the resistance of this metal wire AC, that is nothing but P, must be directly proportional to length of AC. Length of AC is equal to what? L, okay. Similarly, the resistance of the remaining part of the wire, that is Q, I am calling here, Q must be directly proportional to what is the length of remaining wire, that is 100 minus of L centimeter. Both I am taking in centimeters, the ratio will remain same, okay. Q, that is the resistance of this metal wire CB, that is directly proportional to length of that, which is equal to 100 minus of L, okay. Now using these two, see here, I can write P, I take it to the right side, I can write R divided by S, S I will take it to the left side here, or I can write S is equal to what? Q, I will take it to the left side, Q into R divided by P, okay. S is equal to Q into R divided by P. So by this here, what is this Q divided by P? Let us take the ratio of Q divided by P, yes. LHS divided by LHS must be equal to RHS divided by RHS, hence I can write. So let this be equation number 1, let this be equation number 2. Let us divide equation number 2 by equation number 1. So LHS of equation number 2 by LHS of equation number 1, that is Q divided by P is equal to what? That is equal to 100 minus of L whole divided by L, okay. So whatever this Q by P is there, that I can replace by 100 minus L by L. So I can write S is equal to Q by P is equal to what? 100 minus of L whole divided by L into R, Okay, so this is the equation for resistance of a unknown resistor. Okay, this is how we can find out unknown resistance by using meter bridge, by balancing the meter bridge here.